Hello, in this video I'm going to solve the following diamond level problem. One variable calculus, definite integrals. This is a problem from India. Solve the following equation for x. Integral from 0 to 2 times the floor of x plus 14, the fractional part of t over 2 dt equals to the integral from 0 to the fractional part of x, the floor of t plus 14 dt. For every real number a, this symbol, read the floor of a, is the greatest integer smaller than or equal to a, and curly brackets a, curly brackets closed, read it, the fractional part of a is defined by this relation. The fractional power of a equals to a itself minus the floor of a. Pause the video at this point and give it a try. Okay, let us try understand what the problem is. So if you look at the left side integral, this is a function of t, and when you integrate it and then put this calculated in this interval from 0 to this expression, you will get an expression of x. So finally this integral is a function of x. The same is true for the integral on the right. So if you want to understand this equality in a better way, you have a function of x on the left, you have a function of x on the right, you equate them, and you want to find those values of x for which the left side equals to the right side. So it completely makes sense. Okay, but the problem is to calculate these functions of x on the left and on the right. If you don't mind, let me start from the integral on the right because it is very simple. Okay, the first thing that you have to know is that even though at the moment I don't know what x is, but whatever x is, I can say something about the fractional part. So as discussed in the problem, as it mentioned in the problem, the fractional part of x is defined to be x itself minus the floor of x. So definitely this is at least 0, and it is bounded above by 1. It cannot reach to 1. In the second integral on the right hand side, the variable of integration t is supposed to run from 0 to x, the fractional power of x. So in other words, for this right hand side integral, I know that t is somewhere between 0 and that fraction part of x. But as I just told you, the fraction part of x is always smaller than 1. So as far as the right hand side integral is concerned, the floor of t is just 0 because t lies somewhere between 0 and 1. And we already know a formula for this floor function. We know that a plus n, if a is any real number and n is any integer, the floor of a plus n can be written as the floor of a plus the integer n outside the floor sign. Okay, so that's also true for the floor of t plus 14. Because 14 is an integer, so I can write it as the floor of t plus 14 outside. But we just realized that for this integral, this floor of t is 0, so this is just 0 plus 14, which is 14. So the right-hand side becomes equal to integral from 0 to the fraction part of x, but instead of this expression, I can just simply put constant 14 and then dt. But a primitive function for 14 is just 14t, but I have to run 14t from the lower limit 0 to the upper limit fraction part of x, which becomes 14 times the fraction part of x. So let us register this for the future. This is 14 fraction part of x. So that is exactly what I have for the right hand side. So it was very simple. So as we predicted, by the way, the right hand side became a function of x. Now to calculate the left hand side, Okay, let us see what is this function. According to the definition, the fraction part of t over 2 is equal to the expression 1 over 2t minus the floor of 1 over 2t. Okay, and then here the integral goes from 0 to 2 times an integer, because the floor of x plus 14 is an integer. One possible way of solving the problem is to breaking this interval of integration to subintervals in a way that on each subinterval 1 over the floor of 1 over 2t is just a constant. Then it means that I don't need to be worried about this part. This part will be replaced by a constant, and every time I have to integrate this function minus a constant over some kinds of interval, which is a subinterval of this interval. Yes? This is one way of doing it, and of course it is possible. But I want to use this problem as an excuse to remind some of you, if you already don't know, a formula for the integral of a periodic function. You might say, why periodic function? Because actually this function is a periodic function. Because whenever we talk about periodic function, immediately we remember the trigonometric functions like sine, cosine, and tangent. Of course, they are famous periodic functions, but this is also a famous non-trigonometric periodic function. So let us talk a little bit about this to understand this better. So let me change my color because that's not part of the solution. Let's say that a is a real number, but this is not equal to 0. And I define a function g of x in this form: a times x minus the floor of ax. In other words, I am defining the fraction part of ax. My claim is that this function is periodic and its period t is equal to 1 over absolute value of a. In other words, I am claiming that the period of this function is either 1 over a if a is positive, and minus 1 over a if a is negative. Okay, let us prove this claim. In order to prove the claim, I have to convince you that g of x plus this t that I proposed for all x in R, I'm assuming that the domain of my function is R, is equal to g of x. In other words, I have to show you that for whatever x you have in the domain of your function, if you add the period of your function to it, it goes back to itself. That is the meaning of being periodic. So let us double check that to see that it is correct. I start from the left hand side. What is g of x plus t? It means that go to your function, this is my function, replace every x here and there with the expression x plus t. But t is either 1 over a or minus 1 over a. So in other words, I have to replace x with x plus or minus 1 over a. So let us do that. I have a, instead of x I put x plus or minus 1 over a, and then I have minus the floor of a times x plus or minus 1 over a. And then let me multiply a inside, so it becomes ax plus or minus 1 minus the floor, I multiply a inside, it becomes ax plus or minus 1. Then I will continue a little bit, so it becomes ax plus or minus 1. And I will use this formula again, yes, because here ax is a real number, but both plus or minus 1 are both integers, so I can pull it out from the floor sign. Okay, so what happens, it becomes minus the floor of ax, but because of this minus sign, if it is positive, when I pull it out, because of this minus sign, it becomes negative 1, and if I have negative 1, because of this minus sign, when I pull it out, it becomes positive 1. So instead of plus minus 1, it becomes minus plus 1. So that is very good, because plus or minus 1 will cancel minus or plus 1. Yes, because this means that if you choose the positive 1, this one will be negative 1, they are cancelled, and if it is negative 1, this one will be positive 1 and they are cancelled. And what is left for you again is ax minus the floor of ax, and that is exactly your g of x. Okay, so we realize that this function is periodic and this one is its period without being any trigonometric function. So now if I go back here and look at this function involved in my integral, is this function periodic? Yes, because if you compare this structure with this structure, of course here the variable of my function is t, and now you compare and you realize that this a is being played by this 1/2. So if I ask you what is the period of this function, you will tell me that the period is 1 over absolute value of 1 over 2, which is nothing except 2. So the function that I have is periodic. Okay, and again, you might say that, okay, why even we need the function to be periodic? So look, here I have a periodic function, and then this is an integer multiplied by 2, but 2 is exactly my period. Okay, so this reminds some of you might be about the formula of integral of a periodic function. If you know it, you can just immediately skip this part of the video. If you don't know it, let me just describe it for you on the next page. Okay, so now let me again change my color because I want to derive a formula for you. The formula is this. Oh, sorry, I don't know what happened. Okay, the formula is this. So let us say that the function f is a function with domain R, and it is periodic with period, let me change my color. Let us say that f is a periodic function with domain the set of real numbers, and let us say that t is the period. And let us say that alpha is any real number and n is any integer. The claim is this. The claim is that integral from alpha to alpha plus n times t f of t dt is equal to n times integral from 0 to t f of t dt. This is a very elegant formula for the integral of periodic functions. Okay, so this is what I want to prove for you. First of all, if I have to prove it, because alpha is fixed, but I want to prove it that this formula works for every integer n. Okay, if n is 0, there is nothing to prove, because if n is 0, the right hand side becomes 0 times that integral, which is 0. And if n is 0, this is gone, but integral from alpha to alpha of that function again becomes 0, so the left hand side 0, the right hand side 0, it's already done. So let us assume that n is not 0, because for 0 we did it. Now let us do it for only natural numbers. Okay, let us consider the case that n is natural number, positive integer. I want to prove this statement using mathematical induction on n. So let me give this statement a name. Okay, so let me call this statement Q of n. My goal is to prove the statement Q of n if n is natural using mathematical induction. So the first thing that I have to do is to check the validity of Q of 1. So, but what is Q of 1? Q of 1 means replace n everywhere with 1. So the left hand side becomes integral from alpha to alpha plus t f of t dt. The right hand side simply becomes integral from 0 to t f of t dt. This is my question mark. I have to convince myself that this is true. To guide myself about how to do it, Let us try to draw a crude picture here, not very precise one. So let us say that this is the x-axis, and let us say that this is my y-axis, and let us say that this function is a periodic function with period 2, something like this. So let us say that here is t, here is of course 0, and let us say that I have a periodic function that repeats itself, and the length of the period is t. And let us for the time being consider that alpha is somewhere here, okay? Now, the left hand side tells me that integral from alpha to alpha plus t. So this means here is alpha, but where is alpha plus t? Alpha plus t is, this part is alpha, this part is t, so alpha plus t will go here exactly, yes? So let me also draw this one. This one becomes alpha plus t. So now if I ask you how do you interpret the left hand side, you will tell me that this means the area here, yes? So do you see that? Because from alpha to alpha plus t, I am integrating my function, so it will give me the sum of these two areas. Of course, this is a very special case, but this is enough for me to guide how to continue. I want to prove that this integral becomes integral from 0 to t f of t dt, which is completely understandable, yes, because from 0 to t it means that this area. And of course, because this part and this part have the same areas, because the function is periodic and repeating itself, this is more or less clear from this picture. But this already guides me how to do it. Okay, so let me start from the left hand side of my equality, I mean this one, and write it in this form. I can break interval of integration. Instead of going from alpha to alpha plus t, I go from alpha to t f of t dt, plus then I go from t to alpha plus t f of t dt. Okay? And then, by the way, what I have written here is completely independent from the picture that I have drawn. This picture is just for guiding me, but this is completely rigorous based on the theorems and properties of definite integrals. Okay, now I want to use another property of definite integrals. So you know that if I have an integral from a to b f of t dt, I can subtract the same constant, say c, from the lower limit and from the upper limit, but the price is to add that c to the argument of my integrand. Okay, I can do it the other way around. So this is minus, if I subtract from the upper and lower limits, I have to add the same amount here. But if I add a number to the lower and the upper limit, then I have to subtract it from my argument. Okay, so I want to use this idea of subtraction of the limits here. How can I do that? I will subtract a t here and there. So I would subtract a t from here and here, but the price is that I have to replace this t with t plus t. So let us continue. So I copy and paste the first integral from alpha to t f of t dt, but the other one, according to what I mentioned, I can write it as t capital T minus capital T 0, alpha plus capital T minus capital T is alpha, then the price is to add that capital T to the argument of the function of my integrand. But then, don't you remember what is capital T? Capital T is the period of this function, so then it means that this can be written as f of t itself. Now look what I have. I have integral from 0 to alpha of f of t plus integral from alpha to capital T of f of t. So I can combine them now into one integral and write it from 0 to t f of t dt. And now if I ask you what this is exactly the right hand side of the equality that I want to prove. So this is equal to the right hand side. Okay? So I was able to prove this. So let me put it in a box. So I was able to show that this is indeed the case. Okay, now I assume that k is a natural number. I also assume that Q of k is true. Q of k means go to Q of n and replace every appearance of n with k. So alpha to alpha plus kt f of t dt equals to k times integral from 0 to t f of t dt. So this k of q is assumed to be true. Yes? Now I need to prove that q of k plus 1 is also true. So let me write q of k plus 1 here. It means that I have to replace every appearance of k with k plus 1. So what is this? This is to be proven. This is something I want to prove. Okay, I will start from this left hand side of what I want to prove, and then in the middle of the way I will definitely need to use this assumption. So let us do that. If you don't mind, let me multiply this t here and there. So the left hand side now becomes equal to integral from alpha to alpha plus kt plus t f of t dt. I can break the integral into two integrals from alpha to alpha plus kt f of t dt plus integral alpha plus kt to alpha plus kt plus t f of t dt. Yes? So this from alpha, instead of going directly from alpha to this, I go from alpha to alpha plus kt, and then I go from alpha plus kt to the alpha plus kt plus t. Okay? So, but this one is exactly the assumption that I have. This is equal to k times this integral. So for the first one, I use the assumption of induction. So this becomes equal to k times integral from 0 to k f of t dt. But plus, for the second one, I want to use this idea again, this formula. Okay? So what I will do, I will subtract kt from the lower limit and from the upper limit, but the price is that this t should be replaced with t plus kt. So let me do that. So this becomes integral from alpha to alpha plus t f of t plus kt dt. But if I ask you what is this, this is this is a multiple of t, a natural multiple of t, of the period of the function. So if a function is periodic, it doesn't matter how many multiples, how many natural multiples of the period you add to the argument, this will remain f of t itself. So then I replace it with f of t. So I copy and paste the first term, k integral from 0 to k f of t dt plus integral from alpha to alpha plus t f of t dt, because I can eliminate kt. But now this one is exactly what you see here, which can be replaced by this integral again. And this will be replaced by 0 to t f of t dt. But I have one of these integrals here, k of these integrals here. I've made a mistake somewhere. I don't know why I haven't put... Oh, sorry. This is my mistake. I don't know. This is not letter K, you know. This is T. Yes, because here I use the hypothesis, and this is replaced by this expression, and then you see the upper limit is t. Okay, so now this one can be replaced with this integral from 0 to t f of t dt, and then k of them here, this is also t. I'm sorry about that mistake. That is also t. So then it becomes k plus 1 integral from 0 to t f of t dt, and that is exactly equal to the right hand side. So finally I was able to prove this claim for all natural numbers and of course 0. But in order to complete the proof, I need to also do it for negative integers. So let me do it on the next page. Okay, so far I was able to prove the truth of this statement if n is any natural number. But now let us assume that let n be a negative integer. Okay, I want to prove the same statement again if n is a negative integer. Okay, if n is a negative integer, then what does it mean? Then it means that minus n is a positive, is a natural number. So this means that this relation is valid for minus n, because I was able to show that as far as n that is concerned here is a natural number, this works. Here I am assuming that n is a negative integer, so it is not completely clear yet that this is valid for this negative integer. But because n is negative integer, minus n becomes natural number, and this relation was valid for all natural numbers, so this means that this relation is valid for minus n. In other words, I am certain about the truth of this. Yes? This I know because minus n is natural. Okay, now let us see what I can do. The left hand side of this relation can be written as minus integral from alpha minus nt to alpha f of t dt. So what I did, I actually interchanged these limits and I put an extra minus sign because of that. Okay? Now what I can do, I can add nt here, but the price that I have to pay is to subtract nt here. Okay? So then it becomes minus integral from alpha to alpha plus nt f of t minus nt dt. But again, because minus n is a natural number, I am adding a natural multiple of the period to the function whose period is t, so this is nothing except f of t again. So then it becomes minus integral from alpha to alpha plus nt f of t dt. Yes? Okay, so the left hand side of this expression is equal to this expression. So then I am done. Why? Because this one, I know it is true. Instead of the left hand side, put this expression. Instead of the right hand side, put the same expression. Then this extra minus sign and that extra minus sign will cancel out, and you will get integral from alpha to alpha plus nt f of t dt is equal to n times integral from 0 to t f of t dt. Okay? So we were able to prove this relation for any real number alpha and for any integer n, regardless of being positive or negative. Okay? So now let us go back to the original problem and to see how this will help us. But I will copy and paste this formula with me to the next page. Okay, so this is the formula that we proved for a function f whose period is t and n is an integer, alpha is any real number. This is the original problem. The right hand side we already calculated, and I just copied and pasted from this previous page, and we were doing this. But for this function we also realized that this is periodic with period 2. Okay, so now let us break down this problem. Okay, the right hand side is equal to the integral from 0 to 2 times the floor of x plus 14, and then I have this function, which is a function whose periodic function whose period is 2. Okay, so what I want to do, compare this integral with this integral. Okay, here I want to write alpha to be 0, and of course the period is 2, and I want to call this floor of x plus 14 to be n. I can do that because x is a real number. I don't know what x is, but I know the floor of this is an integer, either positive or negative, so I can immediately call it n, because in this problem n can be a positive or a negative natural number, even the zero. Positive or negative integer, or even 0. Okay, and then this means that this integral is comparable with the left hand side, with alpha 0, t2, and this expression n. So I don't need even to calculate this integral in the hard way, because this formula tells me that the right hand side, sorry, the left hand side, I don't know, I messed this one, this is the left hand side. So the left hand side is equal to n, which is x, the floor of x plus 14, multiplied by the integral from 0 to t, t is 2, f of t, which is this function, dt. But let me now use this definition for the fraction part, so it becomes integral from 0 to 2 t over 2 minus the floor of t over 2 dt. But if t is between 0 and 2, t over 2 will be between 0 and 1, so this means that this floor becomes 0. So I am left only with this part. So this is plus. This becomes equal to x, the floor of x plus 14. A primitive function for t over 2 is t over 2 over 4, t to the power of 2 divided by 4. I have to run it from 0 to 2. But if I run it from 0 to 2, it becomes just 1. So it becomes just the floor of x plus 14. So this means that the left-hand side is nothing except the floor of x plus 14. Yes? So now I want to solve an equation. The left-hand side is this, the right-hand side is this. So I have to know how to solve this equation. Or a little bit simpler, I bring 14 out. Yes, equals to 14, the fraction part of this one. But I just told you the fraction part of any number is between 0, including 0, up to 1, excluding 1. So if I multiply everything by 14, the left-hand side becomes 0, then it becomes 14, the fraction part of x less than 14. But if this is going to be true, if there is some x for this property, then this should be equal to this. So this means that instead of this expression, I can put this. So then it means that 0 less than or equal to the floor of x plus 14 is less than 14. I add minus 14 to all sides. It becomes minus 14 less than or equal to the floor of x less than 0. So this means that I know what is the floor of x, because floor of x is on the one hand an integer, on the other hand it's supposed to be between minus 14 up to 0. So this means that the floor of x is either minus 14 or minus 13 or minus 12 and etc. up to minus 1. So this is the floor of x. Okay, for simplicity of writing, let me call the floor of x m, but I realize that m belongs to this set minus 14, minus 13 up to minus 1. This is the only possibility for the floor of x. Still, it is not guaranteed that all these m's are acceptable, but this tells you that if this is going to be true, the floor of x should be m, which m is an integer in this set. If this is going to be the case, the floor of x cannot be outside outside this set. It should be one of these numbers. Okay, so then what I do, I will take this with me and put it here to find the fraction part. So instead of this, I put m, but of course I know m1 is one of these numbers. Then I divide everything by 14 to calculate the fractional part. So then it becomes m plus 14 is 14 times the fractional part. So if I ask you what the fractional part is, you divide everything by 14, so it becomes m over 14 plus 1. So this is also your fraction part. But still m is coming from that set I already discussed. But we know that x, any number, is equal to the floor of that number plus the fraction part of that number, and I am looking for x. So then it means that x is equal to m plus m over 14 plus 1. So that's it. This means that the solution to that equation is among these numbers. Let me write it a little bit more organized. Let me write m over 14 first, and then plus m plus 1. Okay, be careful. Still, it is not guaranteed that all of these answers are acceptable, but we understood that if x is going to be a solution to this equation, x should be in this form where m is one of these numbers. Okay, so this means that outside these numbers you will not be able to find any solution for your equation, but still it is not guaranteed that all of them are acceptable. You have to really check it out to make sure that it is acceptable. Okay, let me do it on the next page. I will move the information I need to the next page, and then we will finalize the problem on the next page. Okay, so if you remember, we were supposed to solve this equation. We did it. We found these are the solutions, but m should be a number within this one. So if that is their logic, if you are looking for the solutions of this equation, look among these numbers where m belongs to this set. But let us check if all of them are acceptable or not. Imagine that m is a number chosen from here, and you take that m with you and calculate this x. We want to show indeed this is a solution. How should I do that? I have to put it back into my equation to see that none of these solutions is indeed a false root. So what I will do, I will calculate the left hand side, which is this one, yes, plus 14. Okay, but instead of that I can put m over 4, instead of x I put the expression I found plus 14, yes, but m and 1 are integers, so according to the rule I can pull them out, so it becomes the floor of m over 14 plus m plus 1, and I have a 14 outside, sorry, plus 14. Okay, but m is somewhere between minus 14 and minus 1. If I divide by 14, what happens? it becomes between -1 and -1 over 14. So if I ask you what is the floor of such a number, definitely you will tell me -1. So then it becomes -1 plus m plus 1 plus 14. So the answer becomes simply m plus 14. That is your left hand side. And now if I ask you what is the right hand side, the right hand side is equal to 14 times the curly brackets x, which is this one. When I multiply 14 by m over 14 plus 1, I get m plus 14. And then you see that this number is m plus 14, that number is m plus 14. So there is no false root. On the one hand, the solution is among these numbers where m is coming from this set. On the other hand, for all choices of m coming from the set, left hand side and the right hand side match. So this means none of the solutions is a fake solution or is a false root. Okay, so the bottom line is that the solution to that integral equation is all x's of this form where m is one of these numbers. So how many roots are there? 14 roots are there for this equation. I hope that you enjoyed the video and this video was somehow useful. I know this is longer video, but if you already knew about the formula of the integral of periodic function, this video were quite short because majority of the part of this video was related to proving that theorem. Okay, I hope that you enjoyed the video and the video was useful for you. Until the next video, be safe and goodbye. Thank you.